Welcome back to Math 104. We begin our third set of videos. In the last set of videos, we saw how to begin with events, call them E and F, and work our way up to more complicated events such as E union F, E intersect F, and E complement. We also saw how these probabilities are related to one another. We had two rules, the addition rule and the complement rule. As a comprehension check before we move on, let's think, which event has a higher probability? The event, it rains today or tomorrow or both? Or the event, it rains today and tomorrow? If we call the event, it rains today, E, and we call the event, it rains tomorrow, F, then this first event here is E union F, while the second event, that it rains today and tomorrow, is the event E intersect F. In general, the union will have a higher probability than the intersection, unless they both turn out to be impossible and have probability 0. But certainly the intersection cannot have a higher probability than the union, because the union, in general, includes more outcomes. It has more opportunities to occur. This is why the notation for union, this symbol, is suggestive. Think of it as a cup that contains many outcomes. By contrast, the intersection includes fewer outcomes. In order for the intersection to occur, it would have to rain on both days. So there are fewer opportunities for E intersect F to occur than there are for E union F. Here again, the notation for intersection is suggestive. Think of it as a cup that has been poured out, at least partially poured out, and therefore contains less than the full cup. In particular, every outcome in E intersect F already counts toward the occurrence of E union F. Everything that is still in the cup after it has been partially poured out was already in the full cup to begin with. So this is a metaphor, and it might help you to remember which symbol is which. We say that two events E and F are mutually exclusive if they cannot both occur on the same performance of the experiment. In other words, the probability that E and F both occur, P of E intersect F, equals 0. This means that when we write out the events E and F as sets of outcomes, they have no outcomes in common. In other words, E intersect F is the empty event. There are no outcomes in common between these two events. We could also write this empty event by this symbol that we've seen earlier, the null event. You may have wondered, back when we defined the empty event, why it made sense to even talk about such an event. This is why it makes sense to talk about such an event. We would like to have a way of talking about E intersect F as an event, even when there's nothing there, even when it's impossible for E intersect F to occur. In the experiment of randomly selecting a family with 3 children, give an example of 2 mutually exclusive events. Think about this definition and produce an example of 2 events that are mutually exclusive. There are many examples of mutually exclusive events. In one example, E is the event that there is at most one girl, and F is the event that there is more than one girl. It cannot simultaneously occur that the same outcome of the experiment has at most one girl, which means either no girls or one girl, and also has more than one. These cannot both occur. There is no outcome in both events at the same time. Notice how, in this example, E and F are actually complementary. It turns out that F is the same event as not E. But it does not need to be that way. As another example, consider E the event that the second child is a boy, and F the event that there are 2 consecutive girls somewhere in the sequence. By 2 consecutive girls, I really mean 2 or more. Now, these 2 events are mutually exclusive. They cannot both occur, because if the second child is a boy, if the middle child is a boy, that blocks the occurrence of consecutive girls. But there is also an outcome, boy, girl, boy, which is not in E, but boy, girl, boy is also not in F, so we do have that E intersect F is the empty event. There's nothing there, but E union F does not equal the entire sample space. In order for E and F to be complementary, they would have to encompass the entire sample space. To explore the idea of mutually exclusive events further, recall another experiment from the homework. A pair of fair dice is rolled. One is red, the other green. Write the outcome 4 on the red, 3 on the green with this notation. This is just a convention to write red first and green second. But this notation is important. It enables us to distinguish between 4 on the red, 3 on the green, and 3 on the red, 4 on the green. Those are two physically different occurrences. It is quite helpful to write out the sample space as this 6x6 array of pairs of numbers. Now let's define some events to think about. E is the event that the sum of the two values is even, F the event that the red die shows a 2, and G the event that the sum of the two values is at least 9. One advantage of writing out the sample space in this way is that it makes it easy to identify certain events. F consists of all the outcomes that I've just enclosed here in this box. Similarly, G, the event that the sum of the values is at least 9, can be nicely identified by this triangle of outcomes in the lower right corner here. These are the outcomes in which the sum is at least a 9, and they are all here. E, the event that the sum of the values is even, can also be identified, although doing it in this visual way is a little bit more difficult. You have these diagonal collections of outcomes here, but this way of marking up the table does make it easy to figure out how many outcomes are in each of our events, and also how many outcomes are in their intersections. So before going on to the next video, find the probability of E intersect F, of E intersect G, and of F intersect G. And then which pairs of events, if any, are mutually exclusive.